If you've ever tried to really understand computer hardware, you've probably hit a wall. I mean, you can find a ton of information on how a CPU, a central processing unit, works. The schematics, the explanations, it's all out there.
But the GPU, the graphics processing unit, that's a different story. It's a complete black box.
Exactly. The low-level details, the actual architecture that makes modern GPUs and AI accelerators so powerful that knowledge is fiercely guarded.
It's pure market competition. And for anyone who's serious about learning this stuff, that leaves you with two pretty bad options. You can either wade through incredibly dense academic papers, or you can try to take apart these huge, feature-complete open-source projects like VeriGPU.
Right. And those are built to be functional, not to teach you anything. It's like trying to learn how a car engine works by studying a Formula One car while it's racing. It's just overwhelming.
Which is why we wanted to do this deep dive on the Tiny GPU project. It's this beautiful, minimal GPU implementation. It's built in, less than 15 files of clean, documented Verilog?
Yeah, and its whole purpose is just for learning. It cuts out all the complex graphics-specific stuff and just focuses on the core principles of general-purpose GPUs or GPGPUs and accelerators.
It really gives you that essential blueprint. You get to see the engineering trade-offs when clarity is the #1 goal, not, bleeding-edge speed.
So our mission today is to use this project, this source material, as our guide to answer 3 really fundamental questions. 1, what is the core architecture of these parallel systems?
2, how is that idea of massive parallelization, what we call the SIMD programming model, how is that actually built into the hardware, into the silicon?
And 3, what are the critical tricks and mechanisms that GPUs use to get around the physical limits of memory, that memory bottleneck?
Okay, so let's start with the big picture, the macro architecture. Because Tiny GPU is built for learning, it does one thing at a time. It executes a single program, a kernel, from start to finish.
And the way you launch that kernel is actually a really clean reflection of how it works on real hardware. It's surprisingly simple.
It is. First, you load your code, the kernel, into a dedicated program memory. Then you load all your input data into a separate data memory.
Then you have to tell the system how much work to do. So you specify the total number of threads you need, and you just pop that number into a special spot called the device control register.
Right. And once that's all set up, you just flip the start signal high and everything kicks into gear. Now, that device control register, it seems almost trivial, right? It's just holding one number.
Yeah, the thread count.
But separating that control information from the actual data path is a really fundamental design choice. It lets all the other units just focus on execution.
And the most important one of those is the dispatcher. You should think of this as the system's project manager.
That's a great way to put it. It takes that huge pool of threads you asked for, and it organizes them into these smaller, more manageable groups called blocks.
It then sends those blocks out to the available compute cores to be processed. And once every single block is done, the dispatcher raises its hand and says, okay, the whole job is complete.
This separation is just so key. The dispatcher manages the work, the cores do the work, but they both share one massive, massive problem.
Accessing that external global memory.
Exactly. And that's where the memory controllers are so critical. You have to remember, global memory is physically located off-chip, and it is way, way slower than the chip itself.
So you could have 10 cores all screaming for data at the same time, but the memory only has so many lanes on the highway, a fixed bandwidth.
Precisely. The memory controller is the essential gatekeeper. It sees all these incoming requests from all the cores, and it doesn't just pass them along, it actively throttles them. It meters them out based on what the external memory can actually handle.
Okay, so it introduces a delay, a latency on purpose to prevent the whole system from just overloading and crashing.
Yes, that latency is unavoidable. It's just the physical cost of going off chip. The genius in the architecture isn't about getting rid of the latency, it's about managing it in a predictable way. And frankly, optimizing memory access is the single biggest battle in all of hardware design.
Well, speaking of optimization, the project mentions a basic cache is a work in progress. But the reason for it is clear. Efficiency. You want to keep data you use a lot right there on the device in super fast memory.
Right, and SRAM. That cache is just a fast local copy. The more you can read from the cache, the fewer requests you have to send out to that slow global memory.
Which frees up the memory controller's limited bandwidth for data it's never seen before.
Exactly. It reduces contention.
All right, so we have the big picture, the dispatcher setting out work, the memory controller's managing the data flow. Let's open the hood and look inside the core itself.
The core is the engine. It's the execution unit. In Tiny GPU, One core takes one block of threads and processes it to completion before the dispatcher gives it a new one.
And to get all that parallelism inside the block, the architecture makes a really important choice. It dedicates resources for every single thread.
This is the absolute foundation of SIMD, single instruction, multiple data. For every thread in that block, the hardware gives it its own private set of tools, its own ALU for math, its own load store unit, its own program counter.
And its own file of registers.
Yeah.
It's like giving every worker their own complete toolbox.
Right. And the foreman inside the core is the scheduler. Now, in this simplified design, the scheduler is a strict supervisor. It executes one instruction for all threads in the block, perfectly in sync, then the next instruction for all threads, and so on.
But that immediately runs into the problem we just talked about, the memory bottleneck.
Correct. Most instructions, like adding two numbers, they're fast, they're synchronous, but the moment a thread needs to load data from global memory or store data to it, well, that's an asynchronous operation.
Meaning it could take a long, long time to come back. And the scheduler has to be designed to just wait.
It's the single biggest pause in the entire system.
And if we look at the little units that do the work, you can see how they're all connected. You have the ALUs, the arithmetic logic units. They handle the basic math, ADD, SUB, multiply.
But they also do the really crucial comparison instruction, CMP.
And that's key for making decisions, right?
Vitally important for any kind of control flow. CMP compares two registers, and it doesn't just give you a number. It sets these little status flags. Was the result negative, 0, or positive? And it stores that result in a tiny NZP register.
Which sits right next to the program counter, the PC. The PC normally just ticks up by 1, moving to the next instruction, but it's always watching that NZP register.
Because the branch instruction, BRNZP, is the only way you can do loops or if statements. It looks at the flags set by that CMP instruction, and it will jump to a different part of the program, but only if the condition is met.
Meanwhile, you have the load store units, the LSUs, and their only job is to talk to that global memory. They handle the LDR and STR commands, and critically, they manage that long asynchronous wait.
They're the ones who signal back to the scheduler. Okay, the data you asked for 100 cycles ago, it's finally here.
Now, we have to point out a huge simplification tidyBPU makes here, but it's for a good reason. It assumes all threads always move to the same program counter value after every instruction. They never disagree.
Which in the real world is almost never true. That's called branch divergence. If one thread's data tells it to go left at an if statement and 7 others go right, you have a huge problem.
Because you lose parallelism. You have to run both paths, one after the other.
Exactly. Managing that in hardware is incredibly complex. So by just assuming it doesn't happen, tinyGPU makes the scheduler design way simpler so we can focus on the core SIMD idea.
And that simplicity carries over to the instruction set, the ISA. It's a tiny set, just 11 instructions. But the real magic isn't in the instructions themselves.
No, the secret sauce is in the registers.
Right. You have a bunch of general-purpose registers for your calculations, R0 through R12. But the last 3 are special. They are read-only, and they are what makes SIMD work.
These registers provide the unique identity for each thread. You have %block IDX, which tells the thread which block it's in. You have %block dim, which is the size of the block. And the most important one,
%thread index. It tells thread number 3 that it is, in fact, thread number 3.
Without those 3 registers, every thread would be identical. They'd all try to load data from the exact same memory address. It would be total chaos. They're like parallel GPS coordinates for your data.
So if you follow one instruction through this simple core, you see it goes through 6 very clear sequential stages.
And this pipeline is designed for clarity, not speed. Stage 1 is FFTCH, get the instruction from program memory. Stage 2 is decode, figure like what the instruction means and what signals to send out.
Stage 3 is request. If it's a load or a store, the LSU sends that request out to the memory controller. And then you hit the wall. Stage 4, wait.
The unavoidable stall. The entire core just has to sit there and wait for the memory controller to send the data back.
Once it finally arrives, you get to stage 5, execute, where the ALU might do a calculation. And finally, stage 6, update, where the result is written back to the registers.
And that model going through all 6 stages for one instruction before even starting the next one, that's the trade-off. It's slow, but it's incredibly easy to follow and debug.
Okay, let's see it in action. The kernel examples in the source code are where this all comes together.
They really prove that this simple ISA and those special registers actually work.
Let's take the matrix addition example. It adds 2 1x8 matrices, so you have 8 threads, and each one is responsible for adding one pair of elements.
And the first thing the code does is figure out which element each thread is responsible for. It runs a little calculation. I, block EX, block dim, plus thread AX.
So it uses an MUL instruction and an ADD instruction.
Yeah.
And because each thread has a unique percent thread at EX in its special register, they all calculate a unique index ID.
Right. Thread 0 calculates I as 0. Thread 1 calculates I1, and so on. They all run the exact same code, but their unique identity registers give them unique results.
Then, with that unique index, each thread does a load, an LDR, to get its element from matrix A, and another LDR to get its element from matrix B.
And both of those LDRs are going to trigger that long wait stage we talked about. The LSU has to wait for the memory controller. Once the data is back, the ALU does the final ADD, and a store, an STR, sends the result back to global memory.
It's a perfect illustration of the whole system. The SIMD principle at work, totally reliant on that asynchronous memory management.
Now, the matrix multiplication example adds another layer, flow control. You're multiplying two 2x2 matrices with 4 threads, which means you need loops.
And this is where that CMP and BR and ZP dance comes in.
Yes. The kernel sets up a label, let's call it LOP. Inside the loop, you do your loads and multiplies, but at the end of the loop, you use the CMP instruction to check if you're done. It might compare a loop counter, k, against the limit, n, which is 2.
So if k is 1 and n is 2, the CMP instruction runs, the result is negative, and the ALU sets the n flag in the NZP register.
Exactly. And the very next instruction is BRNZP. It looks at the NZP register, sees that the N flag is set, and says, aha, the condition is met, I need to jump back to the LOP label. And the loop runs again.
That is the fundamental mechanism. Setting a flag based on data and then making a conditional jump. It's how you get complex logic in this massively parallel world.
So that really connects all the dots, the registers, the ISA, the core units.
Okay, so now for the aha moments. Let's talk about the massive gap between this wonderful learning tool and a real high-performance production GPU.
This is where you see why modern hardware is so complex. I mean, if tiny GPU is a single-lane country road, a modern GPU is a 20-lane multi-level superhighway.
And it's all about hiding that memory latency. So for memory, real GPUs don't just have one cache. They have multiple layers of caches. And more importantly, they have something called shared memory.
Right. Shared memory is this tiny, ridiculously fast block of memory right on the chip that is shared only by the threads within a single block. So if 2 threads need to exchange data, they can do it almost instantly without ever going out to that slow global memory.
It's a game changer for performance. And another huge trick is memory coalescing. Let's go back to our matrix edition with 8 threads. They all request elements A0 through A7 at roughly the same time.
In tiny GPU, that would be 8 separate requests to the memory controller. But a real GPU is smart. The hardware sees those 8 requests are for adjacent sequential memory locations.
Oh, that combines them.
It coalesces them into a single massive transaction. Instead of 8 small lookups, it does one big one. It's like a cashier scanning a barcode for a whole case of soda instead of scanning each can one by one. The throughput goes way, way up.
That's a great analogy. Okay, so what about execution? We talked about tiny GPU's slow, sequential, fetch, decode, wait, execute pipeline.
No production chip could afford that. They use pipelining. Instead of waiting for instruction 1 to finish completely, instruction 2 starts its fetch stage right after instruction 1 moves to decode.
You're streaming the instructions through the hardware, overlapping them. So if instruction 1 gets stuck in that long memory wait stage,
instruction 2, 3, and 4 are already moving through the earlier stages behind it. You're always keeping the hardware busy, hiding the latency of the stalled instruction.
And building on that is warp scheduling.
Yes. Instead of a core working on one big block of threads, the blocks are broken into smaller batches, usually 32 threads, called a warp. A single core can be working on multiple warps at the same time.
So if warp A gets stalled waiting for memory,
the scheduler instantly switches the core's resources to work on instructions from warp B or warp C or whichever one is ready to go. The core never sits idle. It's constantly context switching between these warps to ensure it's always making progress.
And with all this happening at once, you absolutely need coordination.
Which brings us back to control. Especially when threads are using that fast shared memory, they need to synchronize. For that, you use barriers.
A barrier is basically a checkpoint in the code.
Exactly. It's a point where every single thread in a block must stop and wait. Only when the very last thread in the block arrives at the barrier are they all allowed to continue. It's a mandatory synchronization point that guarantees correctness.
So if we pull it all together, what this deep dive gives you is that essential modular blueprint. The dispatcher managing work, the memory controllers throttling data, and the cores with their dedicated
And we
resources.
saw the core SIMD mechanism enabled by those read-only registers like %threaded_x.
But crucially, we've also seen the massive difference between the simple sequential execution you need for learning and the hyper-optimized techniques like pipelining, memory coalescing, and warp scheduling that you need for performance.
Understanding that low-level hardware is the shortcut to really appreciating why modern accelerators are so powerful, but also why they were so constrained by things like memory bandwidth.
And the design choices in tiny GPU,
Hmm.
like ignoring branch divergence or not using pipelining, those were all very deliberate choices to make the concepts clear.
But that leads to the really provocative thought. Imagine you're an engineer. How do you start to integrate those high-performance techniques into this simple model? The moment you add pipelining, for instance, managing branch divergence and errors becomes exponentially harder.
That tension, that constant battle between adding complexity for more speed versus maintaining simplicity for correctness, that is the central puzzle of modern hardware design.
Absolutely. And for anyone who's curious now, the creator really encourages you to go to the GitHub repo. You can install tools like Verilog and Cocotob and actually run these simulations yourself. You can trace the instructions line by line and see the registers update. You can really become the microarchitect.